And we're back for part 3 of section 6.1, learning about inner products. So we'll make up two non-trivial vectors in M22, and then using our inner product from number 5 above, which looked a lot like the dot product for 2x2 matrix, the dot product for R4. We'll find the norm of each vector and the distance between them. So I'm going to let vector A be matrix A and 1, 2, 3, 4, and let's put in some other numbers. 0, -1, 3, and 5. Okay, so the magnitude of vector A would be the square root of matrix A inner product matrix A, which would be the square root of, using our inner product from above, 1 squared plus 2 squared plus 3 squared plus 4 squared. That's 16 plus 9 is 25, plus 5 more is square root of 30. Magnitude of vector B, which would be the square root of B inner product itself, is going to be the square root of 0 squared plus -1 squared plus 3 squared plus 5 squared. And that's 25 and 10 is 35. Okay. And the norm of the distance between them, to find the distance between them, we need to take and subtract the vectors. And so 1 minus 0 is 1, 2 minus a -1 is 3, 3 minus 3 is 0, and 4 minus 5 is a -1. So if we do the magnitude of A minus B vector, which would be the square root of 1 squared plus 3 squared plus 0 squared plus -1 squared, that will give us 9, 10, 11, the square root of 11. Your matrices may be different, so you might get slightly different answers, but you should be able to do basically the same process. So inner products have some special properties. Several of them are not very surprising. So let's go ahead and list them. So if I take the 0 vector and I inner product it with any vector, I should get the number 0, because the inner product is a function, a real valued function. It gives me a number out. The second one is that if I do U inner product V plus W, this looks like one of our axioms, but it's technically not, because it was U plus V inner product W. But the fact that it is symmetric, we could work with it. But this should then be equal to U inner product V plus U inner product W. And you can prove this using the 4 axioms. Okay. Number 3 is, again, similar to one of our axioms, and can be proved using those 4 basic axioms. Number 4, another property. So U minus V inner product W would be U inner product W minus V inner product W. Okay, again, provable by the original 4 axioms. And the last one, U inner product V minus W, unsurprisingly, is equal to U inner product V minus U inner product W. Okay. All right, so there are some basic properties for the inner products that come as natural consequences of the 4 basic axioms. All right, so the standard Euclidean inner product, or dot product, gives us the same amount of emphasis for each component. Okay. However, in many real-life instances, certain components are stronger or more important than others. For example, 10 points on a test is worth more than 10 points on a homework assignment in almost every class that I'm aware of. So what we can do is adapt our inner product to incorporate the strength factors, and we call these strength factors weights. So if we include these weights W1, W2, all the way out to Wn, where each of those guys is a positive number, the larger the positive number, the stronger the weight it will carry. So if we were to take a look at this guy right here, let's do an example. So if we decide to do an inner product, we know that the dot product is a inner product. We proved that on page 1 for R2, or sorry, for R3, and it definitely works for R2 as well. If we throw on some weights, so this one is 1/4 and this one's 1/9, let's go ahead and show that this one is in fact still an inner product by doing our 4 axioms. So the first axiom again is U inner product V. Well, that would be 1/4 times U1 V1 plus 1/9 U2 V2. But a little bit of arithmetic with real numbers would tell me that this is 1/4 times V1 U1 plus 1/9 times V2 U2, which would be what we would get if we did V inner product U. So axiom number 1 is good. Okay, let's go to axiom number 2. Axiom number 2, U plus V inner product W. Well, that's going to be 1/4 U1 plus V1 times W1 plus 1/9 U2 plus V2 times W2. And just a little bit of algebra is going to show me that this is 1/4 U1 W1 plus 1/9 U2 V2, or sorry, U2 W2 plus 1/4 V1 W1 plus 1/9 V2 W2, which is equal to U inner product W plus V inner product W, because it matches up just like it would here. So axiom number 2 works. Let's try axiom number 3. Axiom number 3 was our homogeneity axiom. So K U inner product V should be K times U inner product V. Well, we're going to get 1/4 times KU1 V1 plus 1/9 times KU2 V2. But you can see that we can factor out a K from all of that, getting 1/4 U1 V1 plus 1/9 U2 V2. But that would be simply K times U inner product V. So he works as well. The last axiom, number 4, we need to show that the vector inner product itself, even though it's a weighted inner product, so if we, well, yeah, let's make that equal. So we're going to have 1/4 U1 U1 plus 1/9 U2 U2, or in other words, 1/4 U1 squared plus 1/9 U2 squared. But since these are real numbers and square them, they can never be less than 0. Therefore, this has to be greater than or equal to 0. In fact, 1/4 U1 squared plus 1/9 U2 squared will equal 0 if and only if U1 equals 0 equals U2, but that would force U to have to be the 0 vector. So we have shown that even if I throw some non-negative, or actually positive constants on here, then we get that it satisfies all 4 of our vector space axioms.